So thanks everyone for dropping by. My name is Simon and I'm from this Department of Statistical Science at Duke. And so I'll talk a little bit about recent advances in our group that we've thought about in the area of Bayesian optimization, specifically for physical science applications. And of course, if you have any questions, feel free to just jump in and ask, raise your hand, and I'll answer them throughout the talk or after. All right, so I'd first like to know how to change my screen. Let me just see. There you go. Okay. I'd first like to thank, I acknowledge a few folks that worked hard on this, specifically John Miller, my PhD student who spearheaded both projects, as well as our collaborators from Minnesota, Suo and Sai, and from Berkeley National Lab, Alan and Anne-Katrine as well. So much of our group works in this area called computer experiments, which is basically the virtual simulation of highly complex phenomena via computer code. And so in recent years, our group has worked on various aspects of this, including, using this to design rocket engines for spaceflight, in the area of, particle collisions and high energy physics, or even in designing 3D printed aortic valves for surgical purposes. So you can imagine these experiments are used widely as proxies for actual experiments, which, in many cases is expensive, unethical, or even impossible. But one drawback is that the more complex the phenomenon, the more time-consuming these simulations become. So time and computation becomes a huge factor. Okay. Again, I don't know why my slides is not going. Okay, so one project that we are working on is in the area of real-time engine control for unmanned aerial vehicles. It's particularly, providing control strategies that are stable as it goes through dangerous flight conditions right here. Okay, this is a collaboration between Duke, Minnesota, and the Army Research Lab. Okay. And so our idea here is to use what's called a virtual engine that can simulate, given certain control parameters that I want to use, simulate how the engine performs, how the vehicle performs under different types of control strategies, and simulates this quantity of interest. You can think about this as like engine efficiency, which I'm going to call f of x. Okay. And we're going to then use this virtual engine and put this inside the control software to provide real-time engine control. And so what this is actually doing is like an optimization problem where I want to find control strategies X star that maximizes, right, the engine efficiency. Okay. So right away, there's an inherent challenge, which is that these simulation runs are highly expensive, 10 to the 4 CPU hours for every control strategy. So you can think about it like this, where we start off with control parameters X. We have to run through this really expensive simulator on computational fluid dynamics to simulate these engine quantities of interest. Now, of course, if you want real-time control, you're going through bad weather, right? You don't want to wait 10 to the 4 CPU hours to make a decision. Okay. So this is where we do a lot of work as statisticians, as collaborators, right? We build surrogate models that can, learn this relationship between x and f of x efficiently with uncertainty quantification to guide decisions. Okay. And that's not the last. That's not the end goal. But we're going to use the surrogate model within. Well, we're going to leverage the surrogate model to perform this optimization problem that we need for control. And so this is where this is what I'm going to call, or what's called in the literature, Bayesian optimization. Okay, where you want to optimize, you want to maximize this particular problem, but then the function f of x is going to be very expensive and black box. Okay, so we're going to talk a little bit about this. Another challenge that we face is that, many of these parameters in our computer experiment can be controlled in the simulator, but they cannot be controlled in reality. So I'm going to call these things noise parameters, right? So, in our application here, this can consist of air humidity, temperature, etc. I'm going to call it theta. Now, so in this simulator, we have both x and theta, and it maps this to the quantities of interest f of x and theta. So we can still build a surrogate model here that, is f hat of x and theta. But the challenge comes from the control part, where in reality, I can't really control theta. So we have to think a little bit about how to generalize this framework here to account for uncertainties that are coming from these uncontrollable parameters theta. And I'll talk a little bit about, work that's been done in this area. The last challenge here is this challenge for this need for diverse solutions over the decision spaces. So let's again take our application here. And let's say we had two parameters that we're doing control for, right? Glow plug power, and engine speed. Okay. Now, this plot right here that I plotted out is sort of like a plot for, the quantity of interest, so the engine efficiency. So red here, the more red this becomes, the more preferable it is, the larger the value. So, in this case, it seems like this thing right here is the global optimum, and we want to hit the solution. But in many cases, right, when we're going through flight, there's, varying restrictions over this parameter space. So maybe at that moment in time, we can't really take this decision. Okay. And so we need to maybe identify the other decisions here, maybe this local optimum and this local optimum, to allow for diverse decisions in terms of real-time engine control. Okay, so we need diverse solutions when we're doing optimization. And this idea, this need for diverse optimization really comes from a lot of different areas as well. For example, in optimizing molecular structure for material design, right? You can imagine I use a computer simulator to identify, a promising material structure. Okay, but then we want to identify more than one, maybe like a basket of solutions that we can then take for our experiments downstream in case one of them doesn't work. And so, the model that we use, talk a little bit about the surrogate model. As statisticians, we like to use variants of these Gaussian process models, which some of you may have played around with. And the idea is to place a prior on this black box response surface F. Okay. And so this Gaussian process has two ingredients, right? One is this mean parameter mu, and the other is this covariance function k. So mu controls the centrality of the stochastic process, and k here controls the smoothness of its sample paths. Okay, and of course this is a widely used Bayesian nonparametric framework that's used in statistics and machine learning as well. So let me just visualize what goes on here. Let's say in this case we had one input parameter x. Okay, and I'm going to plot the response on the y-axis. And let's say in this case we run our simulator. Again, data points are very expensive here, right? So we run our simulator at 5 different points. Okay, which I circled here. And so what this process is going to do, or what we're going to have to do, is condition on these data points, right? In which case the posterior process is now in pink, as you see here. Okay. Now the nice thing about Gaussian process is that it gives us efficient closed form expressions. So we get a closed form predictive mean, posterior mean, for predicting what the function might look like at a new point x new. So I'm not going to go through this equation here, but that's what it looks like. We also get a closed form for the posterior variance. Okay. And in fact, we're able to characterize the full posterior distribution in terms of this Gaussian distribution, right? In terms of its posterior mean and posterior variance. And the reason why we like this closed form posterior prediction is that it enables efficient algorithms and uncertainty quantification controls, inverse problems, and we'll see later on in optimization as well. It facilitates very efficient sequential sampling. Okay. And there's been much work recently on, extending this to more deep Gaussian processes. So we've, done a little bit of work on that as well. Okay, so with this fitted surrogate in mind, how do we use this to tackle the optimization problem, right? Let's say in this case, I'm trying to maximize f of x, right, where f is really expensive. So what we're going to have to do is define an acquisition function that quantifies how attractive a new point, let's say xn plus 1 is for optimization. And so one way of defining this is to use this so-called improvement utility function. So I'm going to break this part by part here. Okay, so f max right here, right, is sort of like your current best solution, right? So x1 to xn are the points that you already evaluated the function at, and this is the best possible, the current best solution, f max. And so this function I of x quantifies, in this case, right, if my function f of x is greater than this current best solution, then there's an improvement that I can exploit, right? If it's less than that, then I'm going to just set it as 0. Call this an improvement utility function. Now, of course, in practice, right, we don't know what f of x is. And so what we're going to have to do is take the posterior expectation under our Gaussian process. So that's exactly what this expected improvement idea aims to do. Okay, ei of x. And so we take the posterior expectation under this. And the nice thing about this, again, under a Gaussian process, we get a nice closed form expression, right, for this acquisition function. Now, I'm not going to break this part by part, right, but this is very quick to evaluate. And then the idea is to take this expected improvement and then maximize this to get our next point xn plus 1. Okay, we're going to continue that sequential sampling from there. Okay, so the process is as follows, right? We might observe 5, points right here from our simulator. We compute the EI, right? We get that point which maximizes the EI, and then we sample, right, our next point at that point. And so these sequential samples should ideally converge to the optimal solution, for this expensive function. Now, again, like I said, one nice thing about this EI is that it gives us a closed form acquisition. Okay, and so you can imagine why this is useful, because we have to optimize this EI to get our next point. And if this is in closed form, we can use state-of-the-art optimization techniques, including automatic differentiation and all of that stuff, right, to really quickly optimize this point. Now, in practice, you can imagine there's sort of kernel parameters in our Gaussian process that are unknown and have to be estimated. So typically, the procedure is that we fit these kernel parameters with data, we plug them into the EI, right? And then we optimize this with these plugin parameters, and then this is repeated, right, sample by sample. Okay. Now, one really nice thing about the EI, another nice thing about the EI is that it gives us interpretability as well. So again, let's take a look at maximizing this EI, which involves maximizing these two terms. Okay, let's take this term right here and just take a look at that last term right here, which is S of x, or posterior variance, or posterior standard deviation. In maximizing this, right, you can think about this as favoring points x that has a large posterior uncertainty. So you can think about this as trying to explore the space where we're most uncertain, called exploration. Okay. If we take a look at that first term, and just take a look at this term right here, right? Then maximizing this is sort of like trying to favor points x, which has a large predicted objective. So given our fitted model, we're trying to find the points that maximize that model, right? So in other words, we're trying to exploit our fitted model for optimization. So this is called exploitation. Okay. And so this idea of exploration-exploitation trade-off is actually quite fundamental in reinforcement learning, and this EI criterion nicely captures this. And that's why it's nicely widely used in the literature. Okay, so just to give a flavor, on how EI can actually converge theoretically to the global solution, global optimum here. Okay, typically results take the following flavor. So we've done a little bit of work on this that builds off the work in bulk. Okay, so we have to assume that this function follows, comes from some function class, which we can think about this as the reproducing kernel Hilbert space for our particular kernel that we use for the GP. Assume this is on a compact domain. If we assume certain smoothness conditions on this kernel and under mild regularity conditions, then we can show that, again, the first term here is the objective for the current best solution, right? Over all of the samples that we have, what's the current best objective? This term right here is the objective. It's the global minimum, right? It's f of x x star right here. So this is measuring the optimization gap that we have. And we can prove that this thing converges at a rate of n to the negative nu over d, where d is dimension, remember, and nu is the smoothness of the kernel. Okay, so long story short, what this rate ensures is that it ensures global optimization converges to the true solution with a minimax rate. Okay, so this is nice. One area of interest is that in this bowl result, I'll talk a little bit on a tangent here, right? This bowl result actually requires, now I'll go back a little bit. You recall that in this case, we have to estimate these kernel parameters and plug them in for the EI. And one of the key parameters here is actually this kernel variance sigma squared. Okay. So what bowl requires for this convergence result is that sigma squared has to be estimated not via its MLE, but via n times its MLE, which is kind of weird, right? N is the sample size times the MLE. But this is a condition that's needed to ensure global optimization convergence. So, we thought this was a little bit interesting, and so we reconciled this from a Bayesian, hierarchical Bayesian perspective, which explains a little bit on why you need the scaling in terms of sample size. So I'm not going to talk too much about this, but there's some interesting theoretical work here. Okay, so let's talk a little bit about that second challenge, which is Bayesian optimization with noise parameters. Again, noise parameters here are parameters theta that can be controlled in the simulation, but not in operation, right? And there's really two types of parameters here. One is environmental parameters, things you can't control, like air humidity. Okay. Another is calibration parameters, things that are that are fixed but unknown in terms of the simulator. For example, friction coefficients in the simulator. And so we can model this. One way of modeling this is modeling these thetas as a random variable following some distribution script P. Okay, so you can imagine I have this simulator here where I want to optimize over the control parameters x, but I can't control this, so I'm going to model this as a random variable. Okay. And so that's a problem set up here. Okay, we have our expensive computer experiment here that takes the form of f of x and theta. We can control theta in our simulator. But to account for the fact that we can't control for theta in reality, right? One optimization objective that we could do is to simply marginalize over our uncertainty on theta. Okay, so in other words, one way of doing this is to maximize g of x, this new objective g of x, which is just an expectation of f under our noise distribution. Okay. Now, for the case where f is not expensive, this is known as stochastic optimization in the operations research literature, and there's been a broad work on this. But of course, the novelty here is that this f here is very expensive, and so we can't really apply some of these existing techniques. And so what we want to do here is do exactly the Bayesian optimization procedure, where we want to design these runs x1 theta 1 all the way to xn theta n sequentially in order to maximize this g of x in a sequential fashion with limited runs. So that's the idea. And so what we propose here is this idea called a targeted variance reduction. And so again, there's two parts here, right? One is building the surrogate model, and the other is defining the acquisition function. So let's take a look at the surrogate model first. Nothing too fancy here, okay? So we let f here, f of x and theta, follow a Gaussian process, standard Gaussian process with some mean and some kernel, k of x and theta. It's drawn on both of the variables, okay? And similar to the earlier case, given simulated data, right, of f of x1 theta 1 all the way to f of xn theta n, conditional on such data, we can show that the prediction of the objective g at a new point x new takes, again, this Gaussian form, where these things have, these particular expressions right here, okay? And under the condition, we can show that if our noise distribution is standard normal, okay, and couple this with a kernel here that's the squared exponential kernel, under these two conditions, we can show that this posterior mean and this posterior variance can be evaluated in closed form. Okay, so that's the nice thing about the Gaussian process that we can sort of exploit. Okay, but then you might ask, well, is this reasonable to expect? Well, we can use a squared exponential kernel, it's widely used in computer experiments, so maybe that's not the biggest issue. But the assumption that noise is always standard normal is a very restrictive assumption that's not, realized in practice, right? So we have to think a little bit about this. And so one solution that we've thought about is this, using this technique called normalizing flows, which is recently developed in machine learning. Okay, so the idea here is to find a mapping, right, which takes us from the standard normal, which is on the left, a series of mappings that maps this to our more complex noise distribution P on the right. Okay, and our idea is to learn this transformation I'll call the script T, which takes us from a standard normal to our desired distribution. Okay, now the really nice thing about this is that we don't really have to, this transformation can be learned in an offline fashion, meaning we don't need evaluations on F in order to learn this distribution, right? We don't need these expensive evaluations. We can learn this thing offline, okay? So after we learn this thing offline, we can then reparameterize the objective function. Instead of doing this on F, we're going to optimize F tilde, okay? Where F tilde is just a transformation on our original variables here, okay? So we're going to treat Z as our new noise variables. Now, in order to do that, if you think about this transformation, Z now follows a standard normal by this transformation. And so if we then use our original surrogate on F of tilde, right, then both of our assumptions follow. We have the standard normal, and we can use a squared exponential. And then we make use of this little trick to allow for closed form expressions for prediction. Okay, so that's our acquisition function. Let's take a look, or that's our surrogate. Let's take a look at our acquisition function. Now, keep in mind in this case, our simulator has two parameters, right? Two sets of parameters, x and theta. So our acquisition function has to have both parameters as well, because we have to optimize that. So let's take this part by part here, okay? So let's just take a look at this first term right here. And in particular, let's take a look at this xn star. So what xn star here is defined as the argmax of g hat. Okay, remember g hat here was our posterior prediction of our objective g. Okay, so you can view this thing here as sort of like our best predicted solution under the fitted Gaussian process. Okay, so predicted optimum of this optimization problem. So if we take a look at this first term here as an indicator of g of x greater than g of xn star, you can view this as trying to find points x for which the objective is greater than our best predicted solution, our current best solution, right? So in some sense, we're trying to target this region of improvement where we're improving upon our current best solution. Okay, so that's the first term. Our second term here is known as what's called the variance reduction criterion. This is explored in this paper, Gramercy and Apley. But it's actually quite intuitive, because what this variance reduction quantifies is saying, look, if I observe a next point at x and theta, how much of a reduction in the variance do I get, right, in terms of observing that next point, right? So what's the difference between the variance without that new observations, right, and the variance of the objective after I make that observation? Okay. And so, of course, in this case, we want to maximize this variance reduction as well. And under a Gaussian process, this thing right here can be evaluated in closed form as well, which is really nice. Okay, so the intuition behind this acquisition function is that for promising solutions, we want to find points that increase the precision in the objective G. Okay, and you can think a little bit about this. This need for precision arises from the fact that we have uncertain input parameters, right? And so what this term is doing is it's trying to reduce the amount of variation coming from noise, right? In terms of the acquisition. Okay, so similar to the EI, what we do here is we take the posterior expectation of this I under the Gaussian process, and lo and behold, right, we also get a closed form equation that allows us to do easy optimization, right? We just do this, select the next point according to this optimization problem. It allows us to use gradient-based optimization techniques with automatic differentiation. All good, okay? But it's also interpretable, very similar to the EI. Okay, so if you take a look at this closely, we have this first property, which is exploitation, right? This comes from the fact that we have a g hat of x here. So we want to pick points which have a large predicted objective g hat, right? That's our exploitation. We also have an exploration component, right, on the bottom right here, where we want to favor points with a large posterior uncertainty. We want to explore areas where the function is most uncertain. Okay, the objective is most uncertain. But additionally, we have this additional criterion called precision, right? Where we have this variance reduction term, which tries to improve the precision in the objective G coming from the randomness in the noise parameter. Okay, so all of this is very interpretable with this acquisition function, and this, in some sense, defines a new exploitation, exploration, and this new term, right, precision trade-off for the stochastic optimization problem. Okay. Okay. Now, one thing, when we're doing this in practice is that, oftentimes we can explore parallelized or distributed computing systems for simulations, meaning we don't have to simulate things sample by sample, right? In fact, in a lot of these systems, it's often more efficient to sample things in batches of little k points, right? To pick a batch of 10 points, right, that we want to sample from. And we can easily extend this TVR in the context of these batch sampling algorithms as well. All we have to do is modify this, improvement part by taking the best, right, the best case out of all of the batch sample points, right, greater than the current best solution, and then we replace this with the argmax of G as well. Okay, and under this, we're also able to show, I'm not going to talk about this too much, that this takes in a closed form expression that can be easily evaluated for batch sample. Okay, all nice and good. Okay, so one thing that I didn't talk about was that there is a little bit of a prior existing work on this problem of expensive stochastic optimization. Okay, and much of this work in the literature, I listed a few here, employs this so-called two-stage approach to select this next evaluation point xn+1 theta n+1. Okay, so what they do is as follows, right? They first pick a point xn+1 to maximize some objective. Okay, and this can vary by different methods. And then for a fixed value that I optimize in step 1, I then optimize the theta n+1 to minimize another criterion. Okay, and so that gives us our next point, and they repeat this iteratively to select subsequent points as well. Okay, but you can tell there might be some limitations on this. First of all, this is not optimizing this on a joint acquisition function x and theta. Okay, and so this is not really dealing with the decision space that we want to care about. And perhaps more importantly, because of this, it ignores essential interactions between x, the control parameters, and theta, or noise parameters. right? And you can think about this as follows, right? Because they're, in these two steps, they're not really minimizing the same objective values, right? Or the same objective functions. And so it's not really even guaranteed to converge to anything meaningful. Okay. And I'll talk a little bit about how interactions are actually quite important here. Just a quick comment. Suppose f does not have any interactions, f of x and theta does not have interactions, then this problem right here becomes trivial because we don't have to worry about how the noise varies if there's no interactions, right? So interactions between x and theta are actually quite essential for solving this stochastic optimization problem. And these methods really do ignore it. Okay? And so we'll see that these methods give us suboptimal performance, particularly in higher dimensional problems with more complex noise distributions. Okay, so let's take a look at a quick numerical example here. What we use is this trig test function. Okay, it looks something like this. We have 3 control parameters x, 3 noise parameters theta. And we're going to use 3 different choices of noise distributions. One is just simple, everything is marginal beta distribution. Okay. We're going to use a mixed distribution where theta 1 follows beta, theta 2 follows normal, and just play around with theta 3 follows exponential. Okay. And the last one, just going to go full out complex with this and use this really, weird distribution, right? It's sort of like a Rosenbrock distribution on a manifold, right? At scale to -1 and 1. And so for the first two, we can easily, learn this transformation to the standard normal via just an inverse CDF transform. Nothing too complicated. But the last one here, that's where we have to use normalizing flows, right? Again, we can do this offline, right? To learn that transformation to the standard normal in order to use our method. Okay, so this is a lot of plots. Let me just walk you through this. Now, one thing that I want to note here is that this experiment here is designed so that we do have clear interactions between noise and control. Okay, and this is really just achieved through this term, right? This is our interaction term. Okay, so we should expect that when we have these interactions, that some of these existing methods really don't do as well. We're going to hopefully see that. So on the left plot here, right, we have the beta, mixed, and the complex distribution. And we're going to compare a bunch of different methods. One is just randomly sampling over the space. Okay. This purple one is the standard 2-stage procedure in the literature. We're going to compare with a lot of different other methods as well. I'm not going to talk too much about this. Okay. And then the red one is our method. And we're going to plot this over the optimization gap, okay, as a function of the sample size. Now, remember, in this case, we want to limit the number of samples. The number of samples is very limited. So in this case, we're going to start off with 30 and just go to 90. Okay. So in terms of these plots here, what you do notice is that, again, our method here does the best out of all of these other methods. But in particular, it really outperforms this 2-stage approach, which is in the literature, right? And again, one of the reasons is because these 2-stage approaches really don't define a proper acquisition function and thus ignore interactions between x and theta. And our approach, right, is somewhat able to leverage this to allow for efficient optimization performance, right, with limited samples. Okay, so we see that in this case, this does outperform all existing methods, particularly when the sample size is small. And we tried this for a higher dimension. I didn't show this here, right? But around 10 dimension for noise, 10 dimension for control. This tends to outperform existing methods in that regime as well. Okay, so that's quite promising. Okay, so we then took a look at an application of this. It's a very simple application where we're thinking about how to design brake discs for automobiles. Okay. And so you can imagine, this is quite important when you're driving under variable driving conditions, right? So the design parameters that we're going to deal with is really dealing with the disk properties, the material properties of this disk, right? So thermal conductivity, mass density, specific heat. These things are what we can optimize. Now, there are things that we can control in operations, which are noise parameters. So this might be your initial braking velocity, right, for the brake, and the time until full stop, theta 1 and theta 2. And we can elicit certain noise distributions that capture this. And so I've listed this here. Okay. And so our objective is to minimize the maximum temperature over this braking disk under these variable conditions. Okay. And so we don't have access to an automobile sort of a manufacturer, right? But what we can do is simulate this on computer experiments, right? Namely using this COMSOL multiphysics module. But this is actually quite expensive. It requires around 15 minutes for every material type. So many runs are needed here. Okay, so we start off with 20 runs for initial learning, and then we run this for 80 runs afterwards. Okay. So this is a plot of what it looks like. And I'll mention before I talk about this, that, again, there's known interactions here between material design and the noise parameters, meaning at different types of material design, right? We expect, these noise parameters to have different effects, right? On this, on the response, on the objective function, okay? And so in this case, what we plotted out here is the maximum breaking temperature here, which we want to minimize, remember, as a function of sample size. Again, we're going to compare the same methods here. The two-stage approach, our method, random sampling, and some of these baseline methods. And what you see here is, again, with limited samples, right? 20, 30, and, a little bit going to 33 as well, right? Given this limited sample regime, we're able to hit that minimum breaking temperature much quicker than some of these existing methods, right? And in doing so, this would minimize the cost, right, that you need in terms of this process optimization. Okay, so before I go to the next topic, I know there's been a lot, of material. I'll maybe stop here just for questions if there's any, questions from the audience.
Sure, I have a question. So in the when you have this noise parameter, the objective function you down, it kind of assumes that for every control x, the distribution of theta is
Oh yeah,
right. It doesn't
it's the
depend
same.
on x.
That's right.
What if, can you say more like
What
what
if it
if
does?
the
Yeah,
distribution of noise depends on x?
that's interesting. Maybe chat a little bit about that. I haven't seen that done in the literature specifically for Bayesian optimization. There might be some in the stochastic optimization literature. But what you're saying is that if I change the control strategy, then this noise may also change, right? Um, that's a very challenging problem, right? I would imagine what you have to do is then build a surrogate on how theta also changes in x as well, right? And then integrate that into the procedure. I haven't seen that done, so maybe that's an interesting sort of research direction. Yeah.
Cool. Thank you.
Okay, good. Okay, so if there's no questions, I'm going to move on to the second part, which is talking about diversity for Bayesian optimization. Okay, and so recall that we have this need for diverse solutions from our black box simulator. Okay, and so what our goal here is to find a basket of good solutions that can facilitate diverse decision making. And so, in other words, we don't only want to find one good solution, X star, right here, right? We want to find a basket of good solution. And notice here again, apologies for the notation. Previously, we were maximizing F. But for the sake of this paper here, which we wrote out, I don't want to change all of the minimums and maximums in the equations, right? We're going to now opt for minimizing F. Okay, it's the same procedure, but just a little bit of different notation. But what we have to think about here is what do we mean by good, right? And so one way of defining a good solution are solutions X whose objectives f of x, right, is within an epsilon of the optimal solution. So f of x is going to be less than fx star plus epsilon. Okay. And oftentimes this epsilon here has to be specified from the user perspective, right? Oftentimes you think about this from the domain problem. There's a certain level of specification tolerance that we can allow for, okay? And that's how this epsilon will be specified. Okay? Now we also have to think about how we define diversity, okay? And so one way of defining diversity is to first define, these regions which are epsilon optimal on my parameter space. What I want to do is I want to think about identifying all locally optimal solutions within these epsilon optimal regions as well. Okay. Okay, so let's set this up mathematically. Again, we have this really expensive simulator f of x. We're not going to consider noise here, right? We're going to think about this as a separate problem. And let's think about this from our UAV application, right? Where we have this x1 glow plug power and our x2, which is engine speed. Okay. So remember in this case, right, we talked about, well, maybe this solution here is the best solution. But then we also want to identify this solution here and this solution here. Okay. So what we can do is define the so-called epsilon optimal region, which just takes this optimal solution f of x star, right? This is the best solution, and then ups this a little bit by a certain epsilon. So now we have this epsilon optimal region R of epsilon, but then this also covers a little bit on this solution and this solution as well. We're going to define this as script R of epsilon. Okay, we're going to call this objective threshold of f of x star plus epsilon as f star, right? That's our objective threshold that we want. Anything above that, we don't want those solutions. Okay, so given this, we can say, well, we want to find all local optima, right, within these epsilon optimal regions, R of epsilon. So this allows us to find not only the best possible solution x star, but also these diverse solutions x, I'll call it xn, for lack of better notation, right? X tilde 2 star and x tilde 3 star, right? And I'm just going to denote this here, by trying to find the argmin of epsilon, right? This is going to denote trying to find all of the local minima within the epsilon optimal region. So in this case, I might have capital K solutions. Okay, that's a new optimization problem here. And I would say, in this particular realm, there's been not a lot of work on this. There's been a recent work in AI stats which talks about this rank ordered Bayesian optimization with trust regions called robot for short. It uses a bunch of fancy techniques here on trust region and rank ordering, but then we found that when we applied this, it really doesn't work too well in our regime where we have very limited samples from our simulator. I'll talk a little bit about this later. And there's been other, aspects of this problem that are related in robust black box optimization, but it's not, it's not exactly the same. It's quite distinct from this diverse optimization problem. Okay, we'll compare with this later. Okay, so to tackle this, what we do here is we propose again, this diverse expected improvement or DEI, right, where we extend the EI procedure to tackle this diverse optimization problem. Okay. And this acquisition function is going to what's going to tackle two intuitive goals. Okay? So the first goal, if you think about it, would be to first estimate these epsilon optimal regions are epsilon. We want to be able to pinpoint what these regions are first. Okay? Then after we pinpoint this, we want to identify what are promising solutions within each of the R epsilons. So it's really two goals. Okay, we should treat them as such. Okay, so let's take a look first at goal 1, where we want to estimate these epsilon optimal regions. Okay, and let's make this simplifying assumption that we actually know what this objective threshold f star plus epsilon is. We know what this is. Okay, now given that that's the case, let's call this thing f star plus epsilon, this desired contour, to be A. Then there's a body of literature called contour estimation or contour learning, which thinks about sequential sampling to target a contour of a black box function. And we're going to make use of this Ranjan et al. Paper in technometrics. And so what they propose is a utility function that looks something like this. Now, again, it looks a little bit complicated, but it's actually quite intuitive. Okay, let me just walk through this step by step. The first part of this utility is this part right here, right? Minus fx minus a squared, right? And so to maximize this, right, we want points that are going to be close to the contour with f of x is equal to a. Okay, and so this part right here is going to try and target points where the x's are close, right, to the desired contour. The next part here, right, is based on the posterior variance of my fitted function. Okay, and we're trying to maximize this. So you can think about this as trying to target points with high uncertainty on the contour. We're trying to use this to explore all possible contours, right, which have f of x is close to a. Okay, this is doing an exploration or improving diversity, right, on this particular optimization, on this particular utility function. Okay, so this is trying to tackle the specific contour learning problem. Okay. And of course, in practice, in our problem, we don't really know what the contour is, right? We don't know what the best possible solution, but we can estimate this by the current best solution. So that's what we're going to do here. We're just going to plug this thing in. Okay. So with this in mind, what we propose here is this so-called diverse improvement utility function. And so what we're going to do is we're going to integrate what we just learned about the contour learning acquisition, and also try to identify, right, promising solutions within these regions of R epsilon. Okay, so apologies for the terrible screening here. But what we're going to do, our strategy, is to take that earlier utility function for contour estimation. We recognize this is the same form right here, this thing as our earlier form, right? Take this form here, but only do this for the case where our function f of x is greater than the threshold that we want. You think about these things as points that have no potential for improving the current solution, right? So within points in this region, there's no potential for improvement. And I'm going to use these points to push the learning of the contours of the function. This idea. So for points on the other end, right, for f of x that's less than the contour, then there is potential for improvement on the current best solution. And again, apologies for the screening here. But what we're going to do here is we're going to apply this particular utility function. And really the key part here in this utility function right here is this part that I'm highlighting, f of x minus a squared. Okay, what we're trying to target is really points of f of x, which is much less, right? Gives you much more improvements over the current objective threshold, right? So this is trying to maximize the improvement for our optimization function. Okay, so you can think about this as twofold, right? In the cases where we don't have any potential for improvement, I'm going to use this to learn my contours. In places where I do have room for improvement, I'm going to use this to tackle, right? Learning and targeting points, which maximizes my improvement. And you notice that there's a bunch of other terms here. All this other term here is just to ensure that this utility function is continuous, right? Nothing more to that. Okay, so that's our new acquisition function. It looks quite complicated, but it's actually quite intuitive. Okay, and I'll even talk a little bit about this parameter lambda, okay, which is here, which is a tuning parameter that can control the degree of diversity in my diverse optimization problem, right? So the larger the lambda, the greater diversity is imposed. Okay, we actually proved this in terms of our paper in arXiv on how this shows diversity, but I'm not going to talk about that here. Okay, so remember the next step here, once we define our utility, is then take the posterior expectation from our Gaussian process. And I'm not going to talk about this equation too much because it's not really that nice, right? But the nice thing here about this is that it is in closed form. Okay, it is in a closed form acquisition function. Even though this looks kind of messy, this can be evaluated quickly, and this allows for quick optimization of our subsequent sample points xn plus 1. Again, we can then hit this with our usual gradient-based optimization with automatic differentiation, and we can extend this using batched experiments as well. Okay, and in fact, if we're courageous and we dig a little bit more into what these equations represent, right? We have this in our paper here, just to flesh out the details. I'm not going to talk about that here. But you're actually able to get a quite interpretable understanding of what this DEI criterion is actually doing. There is one part here, I'm not going to talk about this too much in terms of these equations, but there's one part that we can interpret where it relates to the exploration, where we want to explore regions with high posterior uncertainty. There's another part which relates to exploitation, where we want to exploit regions which have small fitted f hat values, so exploit the fitted model. But there's this last part, which is new, which is diversity, where we're trying to explore, right, new unexplored regions in our epsilon optimal region, trying to find all possible contours, trying to find diverse solutions within our acquisition function, right? And so this defines, again, this new trade-off of exploration, exploitation, diversity for diverse optimization problems. Okay, so let's take a look at a quick example of this. We concocted this so-called 2D Bowles function, which is really, all this is just taking the flipped of a Gaussian density, okay, where the modes of these are what we want to optimize. Okay, so a D with 2 would give you a 4 Bowl function, right, where you have these distinct global optima, right, at these 4 points. Okay. And so we set this tolerance to be just equal to this, and then we compare with some of these existing methods in the literature. So for example, this EI, which is just targeting, right, the pure optimization of F, this existing method called robot. And we're just going to compare this with this baseline of just tackling contour learning without improvement and see how well that does there. Okay. And so one interesting thing, this is something that we talked a lot about in our group, is how do we even quantify how good our method is here? Okay, we need a metric. And so the metric that we settled on is this so-called diversity coverage rate, which is talking about how many solutions we found, how many local epsilon optimal solutions we found out of, sorry, this is the bottom one, out of the total number of solutions, right, which is capital K. So the larger this ratio is, the better it is. And we deem a solution to be found. So in this case, we have 3 solutions. We deem a solution to be found if the optimization procedure puts a point, right, within one of these regions. Right? If I have a point here, then that solution is deemed to be found. Okay. And so the higher the coverage rate, the better. Okay, so let's take a quick look at a few experiments. Okay, so this is with d is equal to 4. So there's 16 solutions here. We compare this with di for various values of lambda. In the end, we settled on lambda is equal to 0.5, gives us the best approach. But we can try for different values. We compared it with the EI, robot, the contour estimation approach, right? And just random sampling. Okay, and so what this plot right here shows is the coverage rate of the solution as a function of the number of evaluations. And so if you see this, right away what you see is that the DI performs much better than the EI as the number of samples increases. So it gives us better diversity in optimization performance compared to the EI, which is just trying to find one single good solution. Okay, it's not surprising. But in fact, what we're able to show here is that this comes at a trade-off, right? On the right-hand side, where we plot, right, on the y-axis, the pure optimization gap. So in this case, we're just trying to gauge how well we optimize that problem in terms of the best solution, okay? The pure optimization gap. And we're going to compare this with all of the methods. And dotted right here is the objective threshold that we're trying to reach, the F star, okay? So you see the trade-off that's happening here, where we see that EI, right, in trying to tackle the best possible solution and find that, it actually does better in terms of the pure optimization gap, right? And DEI doesn't do as well. And so one can think about this as, this improved diversity from the DEI is coming at the cost of pure optimization performance, okay? But in fact, this is not too much of a problem for us, because if you take a look at where DEI becomes less efficient for the optimization gap, it's after it goes below that objective threshold, right here. Once it dips below, then it starts exploring, right? And that's sort of what you expect, right? You want, once you hit that threshold, you want to then explore diversity of solutions rather than honing into the best possible solution. And so you sort of see that's what's happening here. Okay, so we then take a look at this rover trajectory optimization application. What we're trying to do is we're trying to navigate this particular space rover, right, from start to end through this obstacle course, where you can pass through these obstacles right here, these red blocks. But once you pass through, you're going to get a great reduction in terms of speed. Okay, so you want to get here from start to end as quick as possible. And so in this particular case, right, we're going to parameterize this with 6 turn points for the rover, which parameterizes both the turn angle of the rover as well as its velocity. So in total, there's 12 decision variables here. So I just plot down what these turn points might look like and what the path might go to. Okay. And our goal here is to find a diverse basket of quick paths from start to end. Okay, so in this case, I know what this navigation path looks like. So I can definitely tell you that there's 8 epsilon optimal solutions here, right, for these paths, right? Denoted by these particular dotted lines. And we're going to try and find as much of these as we can. Okay, and while this is a simple application, right, you can imagine this has broad uses, especially in this area called path planning, right? Which has been used in space navigation, where you have to run a simulator to navigate a space rover through different mediums, or even in logistics, for example, in Amazon warehouses, where you're trying to navigate a robot right through a particular warehouse, right? And you want to have diverse paths for them doing so. A lot of different interesting applications. Okay, so let's take a look at the results here. Again, on the left, what we show here is the coverage rate of the solutions as a function of the number of function evaluations. Again, we're going to compare with the EI, DEI, the robot approach, pure contour estimation, and random sampling. And again, not surprisingly, right, we see that the DEI, right, gives us the greatest coverage of these solutions. All right, with EI not doing too badly and contour not doing too badly here, but it's definitely less diverse than what the DEI gives. Okay, but again, what we notice here is that on the left or on the right here, it comes at a cost of pure optimization performance, right? Okay, and so what we see here is that again, EI, which targets the best possible solution, is able to get much more optimal paths, right, than the DEI. And that's really the trade-off that comes with diversity here. But again, this is not too big of an issue for us because these dotted lines, this dotted line right here, shows us the threshold that we want this problem. And so once we hit this threshold, which is quite early here, right? Once we hit this threshold, we're then more relaxed in terms of exploring diversity for our optimization problem. And so, just to visualize where the diversity comes into play, what we plotted out here on the left are, representative paths from the DEI from the start to finish, and then representative paths from the EI, right, from start to finish. And we notice that, the DEI indeed gets much more paths that are diverse compared to the EI, right? Although these are not necessarily the most optimal paths as we saw in terms of the performance, right? They are within the epsilon optimal threshold, and they are much more diverse than what we get from the EI. Okay? Whereas the EI in this case, gets good paths, but they only get one or two. And so the idea here is that if we're doing path planning and there's a barrier right here or something that's unexpected, all of these paths will fail, right? And you're going to have no solution. Okay, so just for the sake of time, I mean, we had this, I promise you, that we've applied this for the UAV problem. This is a little bit more nuanced. So I'm not going to talk about this. This is in our paper in archive. But maybe I'll just stop here for any questions. So again, these two papers here, 3 papers technically, one of them is in JASA, the other 2 are in archive. And if you're interested in applying some of these problems, right, feel free to ping us, and we have a lot of this code available as well. Okay. Right, thanks.